Chapter 4, and particularly here, Chapter 4, Section 1, will deal with, I think, the most fundamental theorem in differential equations. It's entitled Preliminary Theorem, and the preliminary theorem is what's called the superposition principle. The superposition principle. And it simply tells us how we are supposed to write the differential equation. If you're looking for a differential equation of higher order, and this is our goal, the previous chapters we've talked about differential equations of order 1, a DE with one derivative in it. Or in chapter 3, you could look at a derivative or a differential equation with a second derivative in it, which the previous problem that we were dealing with, Newton's second law, dealt with the second derivative actually, where you have the force is equal to mass times the acceleration. The acceleration is a second derivative. But what happens if you have differential equations of even higher order, maybe the third order, fourth order? But in particularly, we want to use as a model or a foundation differential equations of the second order. Look at all types of possibilities for those guys. How you write those differential equations for the solutions, how you write differential equation of the second order will be very similar to how you write the solution for third order and anything higher than that. So the so-called superposition principle tells us how we ought to write it, because these differential equations will consist of two types, and the types would be either the differential equation is said to be homogeneous or it's said to be non-homogeneous. The homogeneous differential equation is simply a DE that's set to equal to 0. That's all we mean by homogeneous in that respect. If it's not equal to 0, if it's equal to some other function, then the solution gets very difficult to find. But we use as a foundation and a skeleton to find the non-homogeneous differential equations, we use the homogeneous solution. So we start somewhere. How you write those is the key for this particular section. We start to be able to understand the superposition principle. We start with something from linear algebra, and that is what is linearly independence and what does linearly dependence means. In linear algebra, we talked about linearly independence and dependence in terms of a set. A set in linear algebra is generic for anything. Could be functions. And so here we make an application from the linear algebra and say that we could talk about functions that are said to be linearly independent. Now the idea, we'll go through it and kind of look at the rigor behind it, but in a nutshell, what it simply means is that if you have functions or sets, could be sets of lines or sets of curves, that you don't want any overlap with these functions. If there is an overlap, you only want it to occur one time. It's okay for them to cross, but let them cross just one time, and then, as my grandmama would say, go on about your business, right? So if they only cross one time, that means that they exist independently, that one function does not need the other. But if they keep on crossing, then it may be some dependence there. I mean, why are they overlapping all the time? So if they keep overlapping, it usually means that I can take one function or two or three functions and take some kind of combination of them and write the other function that's involved. And so if that be the case, then I have one function depending on other functions. So ideally, linearly dependent. Linearly independence doesn't matter where those functions are. I cannot ever write this function as a combination of the other guys because they're independent. Now the rigor of it is exactly the same definition from linear algebra. So if you remember that, even if you forgot it, it's still going to be somewhere in your soul. Yes. So we'll dig it out a little bit, and it's going to show up. In this class, the same way as in linear algebra, the same thing on the test. You have to make sure that you know these definitions and be able to write the definitions out verbatimly. right? So same thing in linear algebra. It's the same definition. That's the good thing about it. So here, linearly independence, linearly dependence. Well, we say that functions, a set of functions, said to be linearly dependent on some interval, some open interval I, if there exist constants, C1, C2, all the way so on to C sub n. They're not all zero. That's the definition for linearly dependence. They're not all zero, such that this is a linear combination of those functions with those constants equal to zero. Remember, that implies that C sub 1, comma, C sub 2, comma, and so on, C sub n are not all zero. Well, he says it right there. The constants are not all zero. But that's the implication of it. Because the way you write the definition for the linearly independence starts off the same, but the conclusion is different. Linearly independent, the same setup. I have a set of functions said to be linearly independent on some open interval I if there exists constants, the same premise, such that the linear combination of the functions with those constants equal to zero, same premise, but here the constants, the implication is all the constants are equal to zero. Right? That means there's no overlap. That's what the constants being zero means. Okay? That these individual functions, for linearly independence, they exist on their own. They exist by themselves. They don't need any help from anything else, from any other function. And just try to say that and put it right here again. Functions are linearly dependent if you can write one function as a linear combination of the others. I got some examples down here. In other words, if one function is a scalar multiple of another function, then the set of those two functions would be linearly dependent. Here's an example. We take a set that consists of two functions, f sub 1 and f sub 2. We said that these functions are linearly independent when neither function is a constant multiple of the other. In other words, if you have one function that, say for example, is equal to x plus 1, and then the other function is equal to 5x plus 5. Well, this is a scalar multiple of each other, right? And so if that be the case, then they're parallel. And so well, in that particular case, they would represent the same identical function, and so linearly dependent. Now look at the examples here. A set of functions, f sub 1 is cosine square, f sub 2 is sine square, f sub 3 is secant square, f sub 4 is tangent square. Here, they're saying that these functions are linearly dependent. They're linearly dependent because if you can find scalars, C1, C2, C3, C4, how do you know that you have four constants or four scalars? Well, because I have four functions. If you can find constants, not all zero, such that the linear combination of these functions equal to zero, and those constants are not all zero, then these functions are linearly dependent. Now you notice that there's a combination between cosine square and sine square, right? So cosine square plus sine square equal to 1. So here, if you let c sub 1 and c sub 2 equal to 1, so that means we're going to get 1 here for sine square plus cosine square. And then you know that secant square and tangent square are related by 1 plus tangent square equal to secant square. So just let one of those guys equal to -1. So c sub 3 is -1, c sub 4 is 1. And so basically what you end up with is 1 minus 1 equal to 0. 1 minus 1 equal to 0. All those constants, C1, C2, C3, and C4, they're not all 0. To get linearly independence, all the constants, C1, C2, C3, C4, must equal to 0. And from that, and that's the implication, that's what you end up with, but you started off with C1 times F sub 1 plus C2 times F sub 2 plus C3 times F sub 3 plus C4 times F sub 4 equal to 0. And that implies that C1, C2, C3, C4, they're not all 0. If they're not all 0, linearly dependent. If C1, C2, C3, and C4 are all 0, linearly independent. Right. Here's another example. All right. The set of functions f1 is equal to the square root of x plus 5, f sub 2, the square root of x plus 5x, f sub 3, x minus 1, then f sub 4 is x squared. The claim here is that they're linearly dependent because look at this combination. Is it possible that you can write one function as a scalar multiple of the other functions? If you can, then that means that you have linearly dependent. Right? I got one function dependent on other functions. And obviously, and the thing about finding those constants is, I mean, you just choose. You just look at the combination of such, like a puzzle, and see if it works out. I mean, if it doesn't, if you cannot find any such constants, such that you get 0 for a linear combination, and then it must imply that those constants are all 0. And thus, that would give you linearly independence. So here, f sub 2 can be written as, here's the constant, like c sub 1 is 1 times the first function, plus, here's another constant, you call it c sub 3 to match it with f sub 3. It's 5 times f sub 3 plus 0. Doesn't matter if you got one of those guys equal to 0, but they all can't equal to 0. Right? So 0 times the function f sub 4, and that gives you a combination of such that you can produce f sub 2 or just any one of those functions. Well, I told you in the beginning that we have two types of differential equations: homogeneous differential equation or non-homogeneous differential equation. This is said to be a homogeneous differential equation of order n. It's linear. It's linear. It's linear because here's this value for y is raised to the first power. And then all the derivatives of y are the first powers. First derivative, second derivative, the n minus 1 derivative, the nth derivative. There's nothing squared or raised to the third power or whatever like that. If that's the case, then we say that this is a linear differential equation. The order here is n. It's homogeneous because this is equation number 6. I have a 0 sitting over there. Okay. Now look at equation number 7. The same thing on the left side. But on the right side is equal to g of x. Well, g of x is not the 0 function. So we call this a non-homogeneous differential equation. Now let me tell you, it's going to be easy, well, it will be easy to solve for equation number 6. We got some stuff in place to get that. Depending on how big and bad g of x looks, it becomes difficult sometimes to solve for equation number 7. So we hope for an easy function for g of x. Well, I do. Well, you will too after you start doing some of these problems, right? So if g of x is nice and pretty, then easy to get number 7. If this guy is messy, okay. Okay. So let's see. We talked about linearly independent, linearly dependent functions. If it's possible that you can find the derivatives of those functions, then there's an easier way to determine whether or not the set of functions are linearly independent or linearly dependent. And we use what's called the Wronskian. If you've taken linear algebra, or if you're taking it now, and I don't know if you've taken it right now this semester, if you've come to this, probably not. But anyway, it's verbatim from linear algebra. We dealt with linearly independence and linearly dependence, and then after that we introduced the Wronskian. The Wronskian is no more than the determinant of these derivatives of the functions. So if I'm given functions f sub 1 all the way to f sub n, each column you start off with the function, and then below it you'd start taking its derivatives. Right? So first derivative, second derivative. You go down to the n minus 1 because ideally they want to build a square matrix. And to build the square matrix, you count with this guy. This is not a derivative, but you count them all up, you're going to have like an n by n matrix, so it'll be square. And you can only talk about the determinant for a square matrix. Here's the thing. If it's easy to use this, use this. Sometimes you might be able to just go ahead and look for those constants, C1, C2, and C3, and C4 on your own. And if you can get that, if those guys are not all 0, then you know that you have linearly dependence. The Wronskian, the derivative or the corollary that's associated with it, here it says a theorem, says that if the Wronskian comes out to equal to 0, then you have linearly dependence for the function. If the Wronskian is not equal to 0, then we have linearly independence. And I think that's what's down here below. Okay. So if the Wronskian is not equal to 0, then we have linearly independence. We call the set of functions that are linearly independent, we call those set of functions a fundamental set. Now, why are they called fundamental? Because they will fundamentally form the solution basis for the homogeneous nth order differential equation. And the very neat thing is that if you have a matrix or a set of functions and with their derivatives, to solve that system of derivatives, we use that idea of the fundamental set, and we take the fundamental set and we find simply, toward the end of linear algebra, we talked about the eigenvalues and eigenvectors. You take those guys and the summation of those eigenvalues and eigenvectors would form the solution for a differential system. But anyway, the superposition principle. This is the key. Superposition principle says that if I'm given a differential equation, that the solutions of that differential equation are set to be linearly independent. And these values, y sub 1 to y sub k, are said to be a so-called fundamental set. They're linearly independent. And so the so-called solution to the homogeneous differential equation is said to be, I call it y sub c. Y is equal to, it's a linear combination of these functions that are said to be linearly independent. So c sub 1 times y sub 1 plus and so on, c sub k times y sub k. So this section basically just tells us how you're going to write the solution. That's going to be key. We're not talking about how to get the solution right now, but how do you write it? So just in general, it says the same thing. They just use the word or the phrase fundamental set. So let y sub 1 all the way to y sub n be a fundamental set of solutions for the homogeneous linear nth order differential equation. That was equation number 6. The general solutions had to be written like this. So we call the general solution for the homogeneous differential equation the complementary solution. We distinguish that term because when you solve for the non-homogeneous differential equation, we call those solutions a particular solution. And so we have a linear combination of the homogeneous solution, or the complementary, plus the particular gives us the general solution for that very big differential equation, that non-homogeneous differential equation. So the solution for the non-homogeneous differential equation is said to be the solutions of the homogeneous differential equation plus a particular solution. Well, what's the particular solution? It's based on whatever g of x is, and it could be anything. You change g of x, we change the particular solution. So look at this. So the general solution for the non-homogeneous differential equation is said to be the solution to the homogeneous differential equation first, right? That's the complementary solution, and then plus the particular solution. Y sub p is based on some choice of g of x, and that's just given in the problem. So the general solution for differential equation is said to be the linear combination of the complementary solution plus the particular solution. So we just call y sub c all of this. So this is So in a nutshell, the superposition principle says that the general solution for a non-homogeneous differential equation is said to be the linear combination of the complementary solution for the homogeneous differential equation plus any particular solution for the non-homogeneous differential equation. Now all we do in this section, besides using the Wronskian, is just checking solutions. So here in problems 15 to 22, determine whether the given set of functions are they linearly independent or linearly dependent. So let's take number 16. We're going to use the Wronskian. So the first function is 0, the second function is x, the third function is e to the x. We take the derivative of the function that's listed up top with a derivative of 0. The first derivative is 0, the second derivative is 0. The derivative of x is 1, the derivative of 1 is 0. The derivative of e to the x is e to the x, e to the x. You want to find that determinant. Now, if you haven't had linear algebra, then probably in physics they talked about like the arrow technique or the wraparound method. You can use that. That's fine. Here's something that's for free. If you have a square matrix, which you're looking for the determinant, which hopefully is supposed to be a square. Well, this is like a 3 by 3, 3 rows, 3 columns. If you look at the so-called main diagonal, if all the entries under the main diagonal are all 0, then the determinant is just the multiplication of the terms along the main diagonal, and you're done. And you could have, it could be either everything under the main diagonal or it could be everything above the main diagonal, doesn't matter. But for those 3 entries, if they're all 0, then the determinant is just the product of the entries along the main diagonal. So here, that would just be 0. 0 times 1 times e to the x. Obviously, if you don't have the zeros all under the main diagonal or all above the main diagonal, then you have to find the determinant by whatever method that you've seen before. Okay, so this guy is 0. If the Wronskian is 0, that theorem said that the functions are linearly dependent. Let's look at number 17. Yeah. I'm not going to take the derivative of that one. So f sub 1 is 5. F sub 2 cosine square. F sub 3 is sine square x. What do you think off the bat? Linearly independent or linearly dependent? Why do you say independent? Right. Right. You got cosine squared and sine squared. You start talking about taking derivatives, man. It gets long, right? You take the first derivative, you get negative 2 times cosine times sine. Then take the second derivative. That's the product rule, right? And then you got to find the determinant. You've got stuff going everywhere. I wouldn't do that. It's too much work, right? The whole goal of higher education is to make the work less on you, right? You work somebody else, right? There's a previous example that dealt with cosines and sines. Remember that? And I think it had secant squared and tangent squared. We're going to use that idea. So watch this. That it is possible to say negative 1 times f sub 1 plus 1 times f sub 2 plus a 1 times f sub 3, and I get 0. Right? This is negative 1 times 5 plus 1 times cosine squared plus 1 times sine squared. Right? I'm sorry. I meant 5 and 5. 5 and 5. You get negative 5, yeah, for the other guy, right? Okay. So we get negative 5 plus 5, we get 0. So the linear combination of the functions equal to 0, but not all the scalars, right? Not all the scalars are 0. That implies linearly dependent. Yes, Wes? Any scalars, yeah, whatever you like. It can be a fraction, yeah. Scalar is just any real number, right? So notice here that not all the scalars are 0, because we got c sub 1 is negative 1, c sub 2, 5, and c sub 3 was 5. And so linearly dependent. Okay. Right. If you take, like, ideally number 19, since you got just linear functions, it may be easy to calculate using the Wronskian. We get x, 1, and 0, x minus 1, 1, and 0, x plus 3, 1, and 0. There is a theorem in linear algebra that says that if you have, looking for the determinant, if you have a row of all zeros, the determinant is 0. If you use that arrow technique, you're going to get always multiply it times 0, right? Some number times 0. Right? So this guy is 0. So linearly dependent. Now the next set of homework problems, you want to verify the superposition principle. Verify the superposition principle. So On the test, I have a problem where I asked the previous question, are these functions linearly independent or dependent? So you have a choice. You can either use the Wronskian or you can find those constants. And then I have another question there where I will give you a differential equation, and like here, and they give you the solutions. Then they just simply want you to verify that these solutions are indeed solutions to this differential equation. So verify that the given functions form a fundamental set of solutions on the differential equation on the so-called indicated interval, form the general solution. So just take number 23. Let me see here. 31 is a better one. It's just like 23, but it goes one more step. So I can do 2 and 1 if that's okay. I just want to look at number 31. The difference between 23 to 27 and number 31 is that number 31 is a non-homogeneous differential equation. These problems here are homogeneous, right? They're all equal to 0. So, so I'm going to do what I'm going to do for number 31 is what you would do for 23 to 27. Then plus I'm going to go a little bit further because it's non-homogeneous. So to solve a non-homogeneous, you have to first solve the homogeneous solution set, and then from there you get the particular solution. So since my time is running out, so verify that the given 2 parameter family of functions is a general solution of the non-homogeneous differential equation on the indicated interval. So notice here, y, the solution, you get is really 3 little small solutions. Let me go back to number 23. Let me show you something. 23, verify that y sub 1 equal to negative 3x and y sub 2 equals to 4x are linearly independent. That's the first thing you want to do. And then from there, verify that they are individually solutions. Well, just take the Wronskian, e to the negative 3x, e to the 4x, negative 3 times e to the negative 3x, 4 times e to the 4x. You know, when you're looking for the determinant for a 2 by 2, it's just the crisscross, right? So this is 4 times e to the x. You know, is these two guys, then minus, right, those two guys. So this is minus a minus. That becomes positive 3 times e to the x. And that gives us 7 times e to the x. Is this guy ever equal to 0? It's never equal to 0 for any choice of x, right? For any choice of x that's real. So that implies that e to the negative 3x and e to the 4x form a fundamental set. Another phrase for fundamental set is that they're linearly independent. That's all that means, right? So for that problem, you want to still verify that y sub 1 is a solution here. So y sub 1 is equal to e to the negative 3x. Let's call that y. So y prime is negative 3 times e to the negative 3x. Y double prime is 9 times e to the negative 3x. And so for the problem, I'm going to plug in y double prime here, that 9 times e to the negative 3x. Plug in y prime to be negative 3 times e to the negative 3x. Minus 12 times y, that's e to the negative 3x. Do we get 0? Well, let's see. So y double prime, let's write it back out so I can see it. Minus y prime minus 12y. So this is 9 times e to the negative 3x minus y prime, that's minus a minus, that's plus 3 times e to the negative 3x, then minus 12 times y, that's e to the negative 3x. So let's see, we get 9 plus 3, we get 12 times e to the negative 3x minus 12 e to the negative 3x, that's equal to 0. Right? So we verify that. Do the same thing for the next one. The next one is e to the 4x. Do that same thing. And so check also y sub 2 equal to e to the 4x. Now when you do that, here's what here's what the superposition principle says. That the solution to number 23, remember 23 is a homogeneous differential equation. So we call its solution the complementary solution. So for this problem, y sub c, the complementary solution is said to be c sub 1 times e to the negative 3x plus c sub 2 times e to the 4x. That's the general solution according to the superposition principle for a homogeneous differential equation. Now look at number 31. And then I end on this. I had wanted to cover 4.2, but I worked that previous problem from chapter 3, and so it took me about 20-some minutes. But that's okay. So now look at this solution here. See that c sub 1 times e to the 2x? So e to the 2x is y sub 1. E to the 5x is y sub 2. The particular solution to the non-homogeneous differential equation is 6 times e to the x. Well, let's see. So y sub 1 is e to the 2x. Y sub 2 is e to the 5x. Right? Now what you do here is that we look at the Wronskian. I only do the Wronskian on the homogeneous solution set, on the complementary guys. So this is e to the 2x, e to the 5x. So this is 2 e to the 2x, 5 e to the 5x. So we get 5 times e to the 7x minus 2 times e to the 7x. And that gives us 3 times e to the 7x. It's never equal to 0. So it's the fundamental set. All right? So we're going to check 3 of these guys. You check y sub 1 equal to, bless you, e to the 2x. Check that this is a solution. So I need to find its first and second derivative. So y prime is 2 times e to the 2x. Y double prime is 4 times e to the 2x. So I take the original problem, y double prime minus 7y prime plus 10y. Here I'm setting that equal to 0 because y sub 1 and y sub 2 are solutions to the homogeneous differential equation. They don't necessarily solve the big guy, the non-homogeneous one. This 6e to the x would solve the whole thing. So here I have 4 times e to the 2x minus 7 times 2 times e to the 2x plus 10 times e to the 2x. We check that. It's supposed to give us 0. So we got 4 minus 14 plus 10. We get 0, right? Check y equal to, y sub 2 is equal to e to the 5x. So y prime is 5 times e to the 5x. Y double prime, 25 times e to the 5x. So we plug that in, y double prime, 25 e to the 5x, minus 7 times y prime, that's 5 times e to the 5x, plus 10 times e to the 5x. So we get 25 and 10, that's 35, minus 35 e to the 5x, so we get 0. So what we have so far is that y sub c is equal to c sub 1 times e to the 2x plus c sub 2 times e to the 5x. Now you got to check the particular solution. Check y sub p equals to 6 times e to the x. So y prime is 6 times e to the x, and y double prime is 6 times e to the x. So I go to the original problem, y double prime minus 7y prime plus 10y. You set that equal to 24 e to the x. Verify both sides. Because y sub p is the solution to the particular solution. The particular solution is set to match the non-homogeneous differential equation, right? So y double prime is 6 times e to the x, and that was minus 7 times 6 times e to the x, plus 10 times y sub p, that's 6 times e to the x. So the question is that equal to 24 times e to the x? So we check that. Did you check it? What did you get? 24. All right. So you conclude that y is equal to, indeed, y sub c plus y sub p. That's c sub 1 times e to the 2x plus c sub 2 times e to the 5x plus 6 times e to the x. Now that problem should be very straightforward, very easy, because all you're doing is checking. We're giving you the solution. You just check to make sure that these individual solutions are indeed the solution to the differential equation, okay? And all I'm saying again is just do what I do. I've had people on the test, it never fails. Every year they won't do that problem on the test, and it's just 10 points right there. Just match it up. It's just, I'm going to verify the solution, and that's all you have to do, okay? Thank you. Have a good weekend.